I'm the director of the Center for Enabling New Technologies, CENTC, which is sponsoring the summer school. And so today I'm just going to give you a little discussion on catalysis and organometallic chemistry and catalysis and the role of CENTC along with that. Basically, I want to start with our logo here, okay? Because in this simple logo, what I hope we've illustrated is really the power of catalysis, which is basically an energy diagram. Through catalysis, we can lower the energy, the activation energy of a chemical process. It's an amazingly powerful concept because basically what it tells you is you can use any starting material and go to any product that's a downhill reaction, and through catalysis, you can find a pathway to get there. A low energy, a reasonable energy pathway to get there. What does that do for you? That lets you think about using environmentally friendly starting materials, okay? Renewable feedstocks, non-toxic oxidants, things like that, to get to your product. So essentially, you're able to green the production of all basic chemicals, pharmaceuticals, materials, fuels. And when we say green, we mean two things. Green is an environmentally friendly that people talk about in terms of green chemistry. But even more important, well, not more important, but along the same lines is greening in terms of being cost effective. Because the bottom line is, you can be as green and environmentally friendly as you want, but unless it's cost effective, you're not going to get industry to adopt it. Okay? So you're not going to get anywhere in terms of greening our environment. So this has enormous, then, environmental and economic impact. And because of that, CENTC, the Center for Enabling New Technologies through Catalysis, was funded then as the first Center for Chemical Innovation. So the Centers for Chemical Innovation is a new National Science Foundation program where centers are formed to look at high-risk, long-term problems of large scope and impact. And the goal here is really to get research that is likely to actually lead to innovations. Research results that can lead to new processes, materials, or devices that will enhance the economic competitiveness. Okay? So that's what we're doing as part of CENTC. So just a little background on the history of CENTC. CENTC was chosen as one of the first chemical bonding centers. So before the Centers for Chemical Innovation, the program was previously known as Chemical Bonding Centers. And during that time period, when our center started as a Phase 1 center in 2004, we were known as the Center for Activation and Transformation of Strong Bonds, or CATSB. At this time, CATSB involved 12 investigators when it started from 8 institutions across the U.S. We were able to add an additional PI to Phase 1. And that's a benefit of having a center, is that you can add additional expertise and PIs as you need them. At this point, the center was funded at $500,000 a year for a 3-year period. We went on to compete and become the first chemical center, the first Center for Chemical Innovation, the CCI program, at which point, so they changed their name, and we also changed our name, Center for Enabling New Technologies through Catalysis. You might wonder about why all these name changes. The point is to actually, that the names down here are more accessible to the general public, right? Because we want people, taxpayers in the United States, to understand how their money is being spent. And this better describes, is more accessible to people to understand exactly what we do. So now the center has grown to 16 investigators at 11 institutions across the U.S., and it's funded in an amount of $3 million a year from the NSF for 5 years. What CENTC looks like is shown here. It's really quite a spread out center. Okay, it's a virtual center in that way, that we have investigators spread all across the United States, as shown here. You can maybe will recognize many of the faces. There are also lists, and you can find out more about all of these investigators on our website. But it's really much larger than these 16 PIs. Okay, it involves all the graduate students, the postdocs, many of you are here, our collaborators, undergraduate, high school students and teachers, our advisory board members, and our industrial affiliates. And these are a very important component of CENTC, because if really the goal is to develop technology that industry can then take on, it's very important to have industry involved from the very beginning to give us insight on the directions that we're heading, and then also to take the technology as it develops out to actually apply it in an industrial setting. In addition to this, it's also our summer school sponsor. So I want to thank them again for their donations to this summer school. And finally, it's now each of you. So through participating in the summer school now, you become a part of this grand effort in catalysis. So the mission of CENTC is basically as shown here. What we're trying to look at here is to use a collaborative model to get all of these different groups to work together to really attack catalytic reactions involving strong bond activation that are really address problems of global significance. Energy, most of them are energy related. Any catalysis is really energy related because you're saving a lot of energy in the process. And the ability to selectively synthesize a variety of organic molecules and materials. We also have a broader impact mission, and that's as shown here. It's a lot of that is education directed. It's educating. It's helping inspire high school students and undergraduates to enter careers in science. It is training graduate students and postdocs in methods to identify and address collaboratively problems of significance, major significance. And here's where this summer school fits in. It's really to provide educational opportunities to chemistry students and professionals in the area of catalysis. And finally, we're interested in promoting the public awareness of the impact of chemistry and catalysis to the general public. So what do we work on as part of CENTC? CENTC is a remarkable model in that we think about the research that we're doing and change directions on a very short time scale, so that on a yearly basis we reconsider the projects that we're doing and can change and terminate some projects and start other new projects. Current projects that are going on in 2008, a project on alkane metathesis. This is the idea that you can take different chain lengths of alkanes and switch them to make other chain lengths, so you break carbon-carbon bonds and recombine them. Okay, this is useful then it's been getting a lot of press lately in the idea of using Fischer-Tropsch catalysis to take coal and other feedstocks directly to alkanes. And then once you do that, you get a stochastic distribution. Alkane metathesis can help you redistribute those chain lengths to the ones that are desirable for things like making clean diesel fuel. We have projects, electrophilic oxidation catalysis and methane oligomerization are both directed towards activating CH bonds of alkanes and turning them into more useful materials. So in the oxidation catalysis, we're looking at making alcohols, and methane oligomerization is making long-chain alkenes. Anti-Markovnikov hydroamination of alkenes or aniline from benzene, trying to make these chemicals more efficiently from lower-cost feedstocks. Using metalloenzymes for organic synthesis. Just go through these quickly. Dioxygen, so oxidizing water to make dioxygen. These last three, disassembly of lignocellulose, glycerol deoxygenation, and carbohydrates to chemicals, are about using biomass to make chemicals and fuels. In this, you notice this is a very distributed collaborations. All CENTC projects are collaborations between 2 or more PIs. That can get complicated when you're working across large regions of the country like this, several time zones. We do a lot of collaborations within CENTC using the cyber infrastructure that's available today, a lot of video conferencing, and so you can see that here. Besides email and telephone calls, we also do video conferencing. And as shown here, this is a large meeting. Once a month, we meet as a group on something called the Access Grid, where you can see all these individual sites. So North Carolina, Los Alamos, Wisconsin, basically all of our sites contributing to one meeting and meeting as a group on a monthly basis. We also do meet in person at an annual meeting where we talk about new directions and new areas to go into, and that's shown here, our annual meeting in Seattle, and our next one will be coming up in September again. And that involves all of our graduate students, postdocs, the PIs, the advisory board members, and all of our industrial affiliates. Okay, so let's get down to a little bit more of what we're going to be talking about in this workshop this week. Basically, everyone's familiar with pictures like this showing us catalysis, which is basically lowering this energy barrier. The important things to be concerned about in terms of catalyst development is, first of all, the activity. That's lowering this barrier, right? Getting the reaction to go fast or under more mild conditions. The selectivity is critical. This is getting the reaction to go to exclusively one product, or in a large proportion to one product. This is also very important then in doing asymmetric catalysis and getting one enantiomer out. These people are working very hard on a lot of homogeneous work going on in that aspect. As you go on to some of these other aspects that you need, durability and separability. So the catalyst has to be stable to the feedstocks that you're using. You can't have small amounts of impurities which will poison your catalyst. The separability. At the end of the reaction, you have to be able to recycle your catalyst. These are some places then where heterogeneous catalysts often win. And so what you're going to see throughout the discussions of this week is a variety of different catalyst types. And then there are distinct advantages of one over the other in various of these properties. Okay, in discussing how homogeneous organometallic catalysts fit into this, you can look at this time scale here, and you can see the development of various critical molecules in organometallic chemistry through time. Okay, where we have Grignard reagents coming in, the carbonyls coming in, the metallocines coming in the mid-century here, Kubis's dihydrogen compound. But what I want you to concentrate is over here. In the last, let's say, 60 years or so, we've developed all of these new catalytic processes. Okay? So we can see here, and a lot of you have read about these and covered these in organometallic texts. So we can see oligomerization of alkenes, polymerization, alkene metathesis, hydrocyanation, hydrogenation, carbonylation. All of these then have come across in this relatively short recent history. Okay? So just to kind of remind everybody, probably with the most typical example of catalysis that you've seen in your undergraduate and maybe your first-year graduate studies is a hydrogenation reaction. Okay? And shown here is using Wilkinson's catalyst. And so what the metal is able to do in this case is lower the activation barriers for things like breaking the HH bond in H2 and doing an oxidative addition reaction here to a rhodium 1 center to get to a rhodium 3 center, coordinating the olefin, migratory insertion of the hydride to the olefin, getting to here, and then a reductive elimination of the CH bond to get your product. Right? So detailed mechanistic studies have gone into this. Beautiful studies by Halpern establishing this pathway. Notice as well that this is essentially, you have ligand loss here to get to what I'm going to call a 14-electron intermediate if I ignore the solvent coordination here. Right? So we go 14, 16, 16, 16, 14. You go around this cycle. Okay? These are critical things to understand, like that you have to lose a ligand here. Right? Because that's going to then be important in choosing what type of catalyst you're going to use and what your ligand design is. If you tie up all the ligand sites on here, you're not going to get your catalysis. So all of those factors are going to be important in terms of getting your reaction to go and the selectivity based on these various different phosphines. Along the lines in hydrogenation, many of you are familiar with asymmetric hydrogenation, and this is one example of that that's shown here. Is the idea basically being if you're going to coordinate the olefin to the metal center, and we've shown that here, you can coordinate one face or the other face. And then those diastereomers are going to react with dihydrogen to do the oxidative addition at a different rate. And that's exactly what's shown in this diagram here. Okay, so that you can control to get one enantiomer over the other. This was applied to the synthesis of L-DOPA, which is used to treat Parkinson's disease. That was part of the Nobel Prize in 2001 to Knowles for the asymmetric hydrogenation by this pathway. That was along with Noyori's for doing the asymmetric hydrogenation of CO double bonds, and Sharpless asymmetric epoxidation, all in that Nobel Prize. Now you can see still an effort in asymmetric catalysis is this idea that you need this other coordinating group. So that's still a goal, to try to get those reactions to go without that auxiliary group on there. Okay, and a variety of different chiral ligands that are used in this process. And we'll hear more about that through the talks. Hydroformylation, a huge chemical process carried out in industry, basically adding CO and H2 or formaldehyde across a double bond. Right? In this case, you can see you can get either linear or branched products. Okay? Generally, the linear ones are desirable. In this case, you can notice that just by changing the substrate, you dramatically change the linear to branched ratio. Notice as well, changing the catalyst, going from this catalyst here with triphenylphosphine ligands to a rhodium with a bulky diphosphite. You can go here to a huge, then, preference for the linear form. Okay? That's the type of selectivity you can get with these homogeneous catalysts. Okay? And then you can see that variety of understanding the mechanisms of these reactions. So you're going to hear a lot of talks through this on learning about the mechanism of the steps that go into these catalytic processes. That then can let you go ahead and make breakthroughs in further changing the conditions and making better catalysts, and even going to asymmetric catalysis. Methanol to acetic acid. This is a huge process as well. Worldwide capacity in 2000 was 8 million tons a year. This was developed in the 70s, the Monsanto process using rhodium. The mechanistic understanding in this that was developed in studying this catalyst, that is, that oxidative addition was the rate-determining step, allowed the development of the BP Cativa process using iridium, where now they could speed up the step of the oxidative addition, and now migratory insertion becomes the slow step, and you can use promoters to speed that up. Okay? So you can see 80% of the acetic acid in the U.S. is produced by these rhodium and iridium catalyzed processes. Alkene polymerization, the heterogeneous process developed by Ziegler and Nada for polyethylene and polypropylene. This was a Nobel Prize in the 60s. This went on where a lot of work was dedicated to trying to study homogeneous analogs, and that went on to develop single-site catalysts where you could actually control the microstructure of the polymer. So you could get out, just by changing the design of the ligand, get out, as shown here, either isotactic or syneotactic, basically any variant that you've seen there. You can have designer polymers now, okay, based on these single-site molecules. As you move towards late metal systems, there were some beautiful developments out of the Brookhart group in the late 90s, which allow essentially the incorporation of functional groups now into these polymers, okay, because you can use those with late metals and now make functionalized polymers. Okay, so basically we could keep on going and listing all of these catalytic reactions, but that's what the rest of the week is for, right? So just shown here are some ones that we've thought of and put down on this list with preference, obviously, to some of the ones that you're going to be hearing about in the talks through this. So you can see alkene metathesis. You can see various additions to double bonds with Baker, and you can see all this down the list. We're going to see some Lewis acid and F element chemistry. And so I just encourage you to pay attention to everything during the week. Ask a lot of questions. You have experts in the field on all of these things. So enjoy the week and ask a lot of questions is the advice I would give you. Finally, I just want to leave you with a picture of kind of some of the current challenges and future prospects, again, weighted by some of the things you're going to hear about in this program. Things at the top, these are also particular interests of CENTC. Functionalization of CH bonds, water splitting, conversion of biomass to chemicals and fuels, tandem catalysis, base metal catalysis, right? So getting away from things like rhodium and iridium and expensive metals down to some base metals. If you have ideas on this and want to talk to us more about the research that's going on in CENTC, I hope you'll take that opportunity this week to do that. Also, aqueous phase catalysis and integration with biocatalysis. So you're going to hear about these in various talks today. Looking at actually characterization of the catalyst under the actual catalytic conditions, and looking very closely at what the catalyst structure is. That's really important. Is it a 14-electron intermediate? Is it a 16-electron intermediate? Using high throughput methods. Dow has done just amazing with using high throughput to look at catalyst development, and we're going to hear about some of that work this week. Using computational methodology in catalyst development. We're going to hear about that. I think that's on tap for tomorrow. And obviously, engineering is critically important in all of this, right? Because you want these to be industrially useful, right? That's why we're trying to do all of this stuff, so we can actually green chemistry. And so we're going to hear a lot about engineering concepts from Susanna. And finally, I just want to leave you with the idea that even in developing molecular catalysts, you then, in many cases, want to then immobilize those catalysts. And there's been a lot of work recently in that area. And there's a special issue that's just coming out now that Baker was involved in editing that deals with that issue. Because if you can immobilize them, you definitely win on the separability platform. So finally with that, I just want to again leave you with our critical logo here. Welcome to school. And let the games begin.